My name is Avrahami. Thanks, Bracha, for the introduction. I'm working for Advanced Analytics in Intel. Advanced Analytics is a subgroup in Intel of approximately 170 people trying to solve machine learning problems for Intel, for design, manufacturing, etc., lately Mobileye. And this work was a collaboration with Stanford University towards solving a problem that I will introduce in a second. Okay, so today, a lot of people say this is the golden age of data science, the fact that we are sitting here in a conference talking about data science, cyber, etc. So there are thousands of such conferences. So it's kind of the golden age. There are tons of raw data available on the web. Software packages most of them are available online. Relevant models were trained earlier, so you can use them as is, and a lot of public label data sets also available on the web. This on one hand. On the other hand, when you come to real life, on mainly supervised problems, you are facing a problem. Why? First of all, in domain-specific problems, like I will show in a second, the data is much more imbalanced than regular problems like people are building their models for. And I will talk about the problem which is extremely imbalanced. Second problem is that you don't really have labeled data. And without labeled data, you are not lost, but you need to find ways in order to create labeled data or find other solutions like unsupervised solutions. The second problem leads you to a third problem, because once you have a problem, okay, you get, I don't know, 3, 4 great data scientists, and what do? Are they going to label your data in order to build supervised solutions, or are they going to build tools in order to label your data? By the end of the day, you want your data scientists to build models in order to solve the problem, not to label the data. So what can be done? And I will talk about a use case that we solved in Intel. And you know, Intel is selling chips on one hand, but on the other hand, she needs to sell these chips to usually not customers, but usually to companies. And the use case that we have here is we are trying to give insights to the salespeople in Intel. And we are doing it through Twitter. So if a relevant tweet comes and someone tweets it, we want to catch it and give it to the salespeople. For example, if a company that Intel sells to tweets in Twitter that they are going to produce a new product within a month, and it's relevant to Intel, we want to know it, and we want to give it to the salespeople. Now, what's the problem with Twitter? I guess most of you know. Twitter is half English. It's like Twinglish. And here is an example of what it looks like. The problem is highly imbalanced. Approximately 1 tweet out of 10K is relevant. Why? First, because people are, sending a lot of information, not specifically to what we are interested in. And secondly, there are a lot of retweets. Another problem that we are dealing with approximately 10 cases that we care about. For one example here is partnership. So we want to know whether 2 companies are going to do a partnership between them. This is only one use case. There are something like 10 use cases as this. And think about that for each use case, you need to label your data. Of course, you can go one tweet, one after another, and think whether it's relevant for these 10 cases. But anyway, you will need to work hard in order to create 10, or maybe next year it will be 20 use cases that we want to give tweets relevant to this specific use case. So we don't have labeled data, so what can we do? We can label them. It's very expensive, and because it's very expensive, we are trying to find other solutions. And another problem with labeling is that language changes a long time. So once language changes a long time, you need to relabel your data again. This first problem. And second problem is that the definition of the use case might be changed a long time because of business changes and business needs. So what can we do? We can go to unsupervised solutions, or we can go to rule-based. So first thing that we tried is to create rules. What do I mean by create rules? For example, you can see here that we created a rule for the use case of partnership. So we want to know whether a tweet talks about partnership between companies. So if we see the regex of partner or partnering or partners, we will give it you see the score of 0.8. Now, if we see in the specific tweet other things which are opposite to this, for example, months ago or years ago, we will give it a lower score. Okay, so by mixing a lot of regex rules, we can give some score to a tweet, whether it's relevant or not. So this is very basic. Most of solutions is not today, not most of the solutions, but a lot of solutions in industry start from some rule-based algorithm, and that's what we did at first step. So you can see the domain expert, this is usually the leading DS, is defining these rules. It takes time, and by this we got a precision of approximately 0.5. It's not that bad. What it means is that for each tweet that we give to the salesperson, we also give another tweet which is non-relevant. Okay, now think about you as a salesperson. You get, I don't know, a day, 100 tweets. 50 of them are not relevant. It's a bit abusive. I mean, it's not that nice. So what we did, so we went to the crowdsourcing, AMT, Amazon Mechanical Turk, and what we did is we built a tool that we are giving after the rule-based, we are giving the tweets that went out, we give them to the Turks, we call them the Turkish guys, and they are validating for us whether these tweets are relevant or not. And this is a good solution, and we got by this to a precision of 0.85. Now, what's the problem with AMT? First, it's expensive. Okay, we are Intel, but we don't want to waste all our money on giving money to the Turks. Secondly, there is a latency. Once the tweet is being posted, it takes approximately 3 weeks to do this whole circle, to validate the labeling of the Turks and providing it to the salespeople. And thirdly, you need to manage it. Everyone who tried to use Amazon Mechanical Turk knows that it's not just plug and play. You need to validate your workers. You need to define exactly what you want from them. It's not easy. So what can be done? Weak supervision. Anyone who heard about weak supervision? Okay, anyone heard about Snorkel? A bit? One? Okay, so what is a Snorkel or weak supervision? The idea is to take unsupervised data to make some rules, or some what we call weak rules, and to label this data by the weak supervision process. So this Snorkel, and this is the reason that we had a collaboration with Stanford, they built this tool. It's not called Snorkel, of course, it's open source. And we tried their pipeline. The pipeline is based on 2 phases. This is the first phase, and in a second you'll see the second phase. The first phase says, okay, you have unlabeled data. Define you as a DS or as an expert system or as a system expert, define the LF. What are LF? We'll talk in a second, but these are simple rules. Okay, we'll talk about it in a second. And the heart of Snorkel is the generative model. The generative model actually takes the LFs, the labeling functions, find dependencies and correlation and relations between them, and it actually gives you a prediction for each instance. The prediction is the new label, and now you have labeled data. Once you have labeled data, this is the second phase of Snorkel. You can just apply any discriminative model that you wish. If you want a logistic regression, you can do any deep learning model that you wish. Once you have the labeled data. Note that the labeled data is a bit different than usual supervised problems. Here you have the prediction. So it's a float. It's not like a true or false or a black and white. Okay, so we try this, and if you want, what's written here, if you want to retrain, you just start from step 2. Of course, you can add labeling functions as you wish. So I'll talk in a second about labeling functions. They call it data programming, and what are labeling functions? Here there are 3 examples of labeling functions. So labeling functions is the equivalent where in samples you have weak classifiers, right? You have like a tree with, I don't know, 2 nodes. So it's exactly analog to this one. You just define what we call lambda functions or labeling functions, which are simple, and they don't have to be to catch, I don't know, 70 or 80% of the time the correct answer, but you are required that at least in 50% when they are fired, when they give a prediction of 1, they'll be right. Otherwise, your model will not work. So in this example, you can see the first LF, it fires 1 if it sees a regex of partner or partners or partnering, okay? So what we can do is we can take the regex that we defined in the rule-based system and just define them as LFs. Okay? That's what we did as first step. And of course, there are other examples of LFs, and you can see them in the Snorkel website, of complex Lambda functions, such as this one. In this one, there is a really classifier behind the scene, which gives a prediction, and it's okay. The Snorkel model will combine everything, will find a dependency between the LFs. So we tried it. We defined the previous regex that we defined for the Turk here. We applied the BiLSTM plus attention for the discriminative model, the second phase of Snorkel. And we got an F1 of approximately 0.1. So it was a bit disappointing. And why it happens, then we had to go back and think about what really happens here, because Snorkel should be good. And then actually the collaboration started. And what we found out that our use case is not that standard, and we need to develop new tools in order to solve our specific problem. So we developed Osprey. Osprey comes on top of Snorkel, and it's a modification of Snorkel. Okay, so this is Osprey, and I will show now the 3 main contributions that we developed in order to solve this specific problem. So first of all, it's kind of technical. So what we did is we built a system that instead of building, very complex labeling functions, we just created kind of a table that you are inserting your regex in order to create the LFs. Okay? Once you put it in the table, we are creating for you the labeling functions, and on top of that, we are boosting the labeling functions. What does it mean? It means that you can see here, for example, in the first one, LF partner, you see the 1 and 2. It means that if we saw 1 or 2 occasions, then the LF will fire. If we saw 2 to infinity, another LF will fire. And by this process, we boost our labeling functions. Another thing that we do is that we created combinations. Okay? We took combinations of labeling functions and created a new labeling functions. This is the automatic way of creating it. Another thing that is important to note, that not only textual data is important here, also metadata about the tweet. So text length, number of handles, number of emojis also can be created, auto-created by our system. This was the first one. The second contribution was in the terms of class imbalance. So what should we done with class imbalance? We created syntactically balanced dataset. What did we do? I said before that 1 out of 10K are relevant tweets. So we created synthetic data, which is approximately 6% out of the full corpus comes from 1. Why it's 1 and not really true? Because it comes from labeled data that comes from the Turks. Okay? So if 3 out of 3 Amazon Mechanical Turk workers labeled such data as relevant, we think it's true. As I said before, approximately 85% out of them are real true. So we create a much more balanced data set and then applied it into the flow. The third contribution that we did is we did ensemble. So in the original paper of Snorkel, the generative model was intended only to use for labeling the instances. What we did is we also added it to the prediction process. So you can see here we are creating 10 discriminative models and add it to the generative model that originally wasn't built on purpose to give the final model. So we combined them all, and we got this new flow. As you can see, synthetic data is inserted into the model instead of the original data. Here you can see that we are creating the LFs automatically. And thirdly, we are using the generative model for the final model and not only the discriminative model. Experiment. So what we did, we built 3 systems. System 1 was rule-based, based on AMT. This is the process that we had before. The second one was a weak supervision, which is Osprey. And the third one was a full supervision, based on a very small data set that we had, which was labeled. I will not take you through the whole process here, but must say that all 3 systems had the same domain knowledge and used the same deep learning model, which was by LSTM. Plus attention. I will go through this one. This slide tries to show the ensembling effect. Each row here is a generation of, the last row is actually the final model that we got, and you can see that the precision here is very close to the rule-based. Now, we are not aiming to win the rule-based, but we must say that rule-based solution based on AMT process is not feasible. I mean, as we said before, it costs money, latency, management, etc. But we are trying to get as close as possible. These slides show that ensembling really helps, and these are the final results. You can see each partnership, product launch, and M&A are 3 scenarios that we care about, and in each one you can see the precision of the model that we got. You can see that in the middle one, the precision was a bit lower than the fully supervised, but it depends on how you compare it. Generally speaking, the performance of the final model was much better than we expected, and it's currently in production. I thought to show the system, but it's not connected to my PC, so problematic a bit. Generally speaking, so Osprey results are better than equivalent supervised, and it's close to human, okay, to AMT plus labeling. You don't really need to label the data, no crowdsourcing along the process, and although we demonstrated on text problems, Osprey and Snorkel in general are very relevant to any principle that you can think about, images, general classification problem, etc. Once you have unlabeled data, you can apply Osprey or Snorkel to solve the problem. That's it. The paper was presented this week in a conference in Amsterdam. You can search for Osprey in Scholar and look for it, and I'll be happy to answer any question you have now and after the talk. Thanks.
היי. רציתי לשאול לגבי, I wanted to ask about the synthetic data generation. So what's the technique there? Is it configurable? Is it smooth, Adasyn? How do you generate the synthetic samples? And then another question is in the table, the benchmark table that you presented. So you got close to the precision column, but the recall was also affected, which is also something that is, I think, meaningful, especially when we're talking in imbalanced data scenario when you get a lot of false positives.
Okay, so great 2 questions. So first, regarding the synthetic data, so it was a long experiment how to find the real balance. So the secret here is how do you, what mixture do you do? So of course you can take, general population from Twitter and just add it to your corpus. But what we did is we also take what we call anti-scenario. So we took data which was labeled as 1 in another scenario and put it as 0 in the corpus that we created. And of course, the balance, whether to take 1%, 2%, 6%, was a very long journey how to find the balance. Regarding your second questions about the evaluation, so it's a really great question. I didn't have time to talk about it, but recall in such cases are not really available to measure because you don't have a full corpus which is labeled. I mean, the only thing you can measure, really measure, is the precision. Because think about it, you have a system, it yields you, I don't know, let's say 1,000 tweets which are relevant. Okay, you can label these 1,000 tweets, but you are not going to label all these million tweets that went into the system. So the recall column that you saw is relative recall. It's relative recall to the baseline, which is the baseline system, okay? So,
thank you, Avrahami.
Okay, thanks.
Thank you.